So thank you very much. Good morning from Greece, from Hellenic Mediterranean University in Crete. It's a great pleasure to have with us Professor Luis Pereira from the new University of Lisbon. I will say a few words about Luis. I will start with what do I know, and then I will read, my notes. So Luis is like an excellent partner of our department, of our university. Always he's supporting our summer schools, I don't know, since 2006. He belongs to a team, to a fantastic research team in Portugal, and this shows to us how small countries, like if they have, a motivation, if they have, a planning, that they can do things, that they are world leaders. So Luis will present us, the work that happens in the new University of Lisbon. I was very lucky to visit once at the university, and I was very much impressed by the work that has been started from few people, but this has made the new University of Lisbon, and particularly this group of people, like world leaders, like they are a reference. So this shows, and this is a nice example for Greece as well, that what we can do if we have a planning and if we believe on what we are doing. So a few words about Luis Pereira. So Professor Luis Pereira was born in Lisbon, Portugal, in I'm not going to say the date. I will keep, the date, He received the engineering degree in material science in 2001 and has finished the PhD in microelectronics and electronic materials in 2008 in the new University of Lisbon. His PhD work was focused on polycrystalline silicon and high-K dielectrics for transistors, TFTs, applications. Yeah. The expertise gains on oxide materials for electronics focused the postdoc activities on the development printed inorganic nanostructured materials for chromogenic electronic and electrochemical devices on paper and plastic substrates. And this is like very essential, because today Luis will speak to us about new functional materials inspired by the nature and their applications in the electronics, and particularly in sustainable electronics. That's a priority based on the Green Deal of the European Union. His work has received more than 3,500 citations, and his impact factor is like 32, even more. He's an editor in a lot of high prestigious journals, including the Nature family, and his current research interests are on the design and synthesis of 1D, 2D, and 3D inorganic and hybrid nanostructures, chiral cellulose, nanocomposite, functional micro and nanofibers, and its integration on chromogenic, electronic, and electrochemical devices. Also, Luis, now he has done the second step, that as a scholar, all of us, not all of us, we're not going to do all of us, but if the progress of your work is like recognizable and has an impact, he works also, if I remember well, like to the industry. So all this technology that he will present it to us, it's right now an industrial product. So Luis, thank you for your time. I know that you are very busy, and we are very happy to have with you, and the floor is yours.
Okay, thank you, Kostas. First of all, I would like to thank you for the invitation. It's always a pleasure to take part on your initiatives. So we have been doing this for several years, as you mentioned, and I will be willing to take part in the future in further initiatives. It's always a pleasure. And also to give the opportunity to share some of the work I did with my team in the past, I would say, 6 years. Also within the frame of ERC grant that I received in 2015, related with these developments on cellulose-based materials for applications in electronics and energy harvesting devices. So I will share my screen, and we'll start the presentation. So the title of my presentation, as Kostas already mentioned, is to give you some insights on how we can use natural materials or nature-inspired structures to create functional materials for electronics. And the goal here is, like you can see in the title, it's to create or to contribute to this new class of electronic devices that are emerging, that are called transient electronics. So this type of devices that aim to, let's simplify, to survive for a short period of time. And to cover these concepts of IoT, but I will show then some of the potential applications of these things. And of course, where we need to think in new concepts behind the conventional electronics that we use for, let's say, long-lasting devices like computers or smartphones. So it's a kind of a rational use of resources and the design of the products and of the electronic devices according to the final application. So as Costas mentioned, I'm also now in a new life. So I still have my position as invited professor at university, but now I'm more or less at full time at a new institution that was created that is called Alma Science. It's a set of, it's one of the labs that were recently created by the Portuguese government that are called collaborative labs. And they basically aim to join research and industry around some topics. And this one is exactly around the application of cellulose for smart applications. Okay, so behind paper and paper for writing and for tissue paper, for instance. And there are several in Portugal, as I said, 26 around different topics. And now I'm leading the scientific part of this new project. And this aims to bring these technologies from the lab to industry, and so to seek next to the industries where these technologies can be really impact and can be used. So to start, after this brief introduction, so I will talk today about why we want to use cellulose in electronics, and then I will show some of the examples of the things we have been doing. So like make composites with cellulose to make functional inks that we use for printing sensors or to print transistors. I will also show that we can produce electrolytic membranes that can be used in energy harvesting devices, but I will focus here also on the application on the electronics, so how we can replace conventional dielectrics by electrolytes, solid-state electrolytes in these devices. And I will finalize with the applications of functionalized cellulose fibers in energy harvesting devices that we can harvest mechanical energy and convert it into electrical energy. So to start, so what is missing? I already said something about this. So of course, we all know these buzzwords of sustainability, but this is becoming more than just a buzzword. It's becoming really a big concern for our society. And we know that, and I will show some numbers, that if we continue the evolution in the design and manufacturing of conventional electronics, we'll hand in a dead hand, basically. We'll stop in a dead hand because we'll have problems in supply of raw materials, and this will be crucial. So when we talk about sustainability applied to electronic devices, of course, we need to consider here three key vectors, like the use of advanced functional biomaterials, so materials that are produced by nature. So they could be abundant, so to seek and to check where we can use these materials, simplify the manufacturing process for some of the devices that we want to make. And of course, think on what we call it eco-design. So having in mind issues like recyclability and disposability. So considering the end of life of the product that typically is not considered or was not considered in the past when you design electronic devices. So some figures about the electronic waste that is generated. So you see here some numbers, and these are fixed numbers until 2016, and then some predictions that I recently revised some recent forecasts, and these are not very different from what is here for the current numbers in 2020 and 2021, the predictions for 21. But it says that in 2016, we had around 45 million tons of electrical waste that was generated. Okay, that it's now above 50 million tons. And growing, because we know that more and more we are being surrounded by electronic gadgets. So this is growing trend. This gives something that is a kind of impressive number. That is a kind of 6 kilograms per inhabitant in the planet of electronic waste that is generated. Of course, the distribution is not even, if you consider the different continents. So you see that in more developed countries, you have more, even more than these 6 kilograms. In Europe, it's something like 16 kilograms per inhabitant. And more impressive is just to think that 45 million tons, it's equivalent to 4,500 Eiffel Towers. Okay, so it's what is being generated every year. But also not only the waste that is being generating, but the losses that we have in terms of materials that are not being recovered. And this is something that, just considering in 2016, is something like 55 billion euros of raw materials that were not recovered. So it's just thrown to a landfill and will be there maybe until the end of the planet without being recovered. So we are creating trash, we are throwing money away. So these are two big issues. And of course, even when you go for recycling, we know that this typically are not following the most convenient and most suitable the recycle streams, and end up at underdeveloped countries doing things like this to recover only part of the materials. And of course, the dream would be to recycle these electronic devices like we do for paper. So it's like a very efficient recycle cycle already. So in Europe, for instance, in average, 70% of the paper is recycled, with a very well-defined lines and very defined cycles and value chains. And so if this would be possible, of course, this would be the dream. Okay, but we are just talking about the dream, not yet the reality. And of course, the idea is also to fit on these that also are nowadays important, the Sustainable Development Goals defined by the UN. And of course, we are here targeting several that are highlighted, like industry, innovation and infrastructure, sustainable cities, climate action, and life on land. But others can also be considered. Okay, so just to frame where we want to be, I have here just one slide, just also to give you a brief introduction on the interest on this, because we don't want, of course, and when we think on these new devices, we don't want to replace the what we call conventional electronics. Okay, so we know that high performance electronics, and those that work in this field know even better than me. It's high performance because it's made under very controlled environment with dimensions that is not possible to reach without some specific tools, very expensive tools, very expensive process. And the chips become, let's say, accessible from the cost perspective because they are produced in large scale and over big silicon wafers. But the processes are expensive, and even the silicon wafers are also expensive. But of course, we don't want to replace these conventional electronics. It will be always a space for these electronics for high performance devices. But just to make a comparison, so if you consider last year, if you put side by side all the silicon wafers that were produced, this would, or processed, this would cover something like 8 million square meters. Okay, per year. So it's more or less the equivalent area of the silicon wafers that were consumed or processed last year. In terms of availability of materials, for instance, if you consider a paper machine producing paper as a substrate for electronics, just a simple machine in one shift in a factory produced the same area. So a machine in 7 hours, a paper machine in 7 hours produced the same equivalent area. Okay. Of course, if you are using a cheap substrate that is easy to produce and it's produced in such large scale, it makes no sense to go and then to use expensive techniques to process electronic devices on top of it. That's where we have this concept of printed electronics, of course, that is known for several decades. So they're using additive process, low-cost process, without the need of clean room, for instance, and you can build your devices with using conventional, I would say, not conventional, but okay, let's assume that are close to what is conventional graphic printing techniques. And of course, in this way, you can also process devices at a faster speed with a low-cost process. Of course, also it's important to consider that we are not going for the same level of integration that you get in conventional electronics, okay? Because in conventional electronics, you have a high level of integration, and the devices by printed electronics are at least, I would say, if you compare a transistor, are at least 1,000 times bigger in area than one transistor processed in, just a single transistor processed in conventional silicon wafers. But of course, as I said, this is also not aimed to replace conventional electronics, it's aimed to create a new set of devices that could serve, let's say, these concepts of IoT and smart packaging and wearables. So where you need really some large area electronics, so where you have some kind of disposable electronics, transit electronics, as I mentioned, so that things that will last for days or even less than 1 day, or will work for less than 1 day, for instance. And so where you need really to be rational when designing the things that you will implement. And of course, you need to look at the market where these could fit. And I used to say always when I give this type of presentations that there are two holy grails, okay? You have the smart packaging and you have the biomedical applications. And why these are considered the holy grail? Of course, smart packaging is where you have the volume. So imagine if you have smart packaging, you imagine the number of packages that are deployed every day around the world. So it's where you have the volume to grow and to get money from it, of course. And the biomedical, it's where you have the margin, the cost margin that you can add to the product. Because when you go to develop this type of systems, of course, you will increase the cost. If you go for a smart packaging, you will increase the cost of the packaging. So it's not always well accepted by the manufacturers and by the producers that you will increase the cost by even by 10 cents or by €1. It's almost impossible to accept it. But there is room in some markets like the biomedical market to have it. Okay, so having said that, we have been working in the past in several types of devices that goes from memory, batteries, displays, sensors, solar cells, electronics on paper. There is the reference of some of the pioneer works that we did around all these topics. And today I will, as I said, talk about some recent activities on making these devices on paper using printing technologies, and also using the paper not only as a substrate, but in some cases, or cellulose materials as a functional layer in these things. And so I will start by showing some examples on the carbon fiber electroconductive inks. And so we made this ink, conductive ink, that is a mixture of carbon fibers with a cellulose derivative. So it's a kind of modified cellulose powder. It's called carboxymethyl cellulose, so it's water soluble powder, and it's good because cellulose is not water soluble, but when you modify it chemically, it may become soluble in water. And so it's good when you want to make inks or upscale this process that you use always water-based, let's say, systems. And so the idea here was to optimize the ink composition, so to find the right amount of carbon fibers, the right amount of CMC, to get the right viscosity properties in the ink that could be printed. And we were using screen printing for this technique. And you can print conductive layers, you can print the sensing layer. So you have the ink that contains carbon fibers and cellulose, okay? And we go to analyze what are the properties of these printed patterns. If you look, we have fibers dispersed in the cellulose binder. So the CMC, it's what keeps the fibers together. You need to adjust the quantity of the carbon fibers that you have in the layers that you are printing, in order to have a percolation path for current, because these will be resistive sensors. So you see that with just one printing layer, you don't have a percolation path. Only above 4, you start to have this percolation path, and it stabilizes around 7. So you need to find the right printing process or printing, let's say, procedure to adapt to find proper conductive properties for printing patterns that you are making. And then also adjust not only the printing, but also the drying process. And here is just an example on how compares the resistivity of these layers if you dry it at room temperature, like you see here, and you dry at 120. So if you force drying, you end up with something that is a pattern that is more, I would say, porous, or where the fibers are not so close to each other, the carbon fibers that provides the conductivity. So this seems to be bad in terms of conductivity, okay? But when you go for applications in sensing, this becomes good. Why? For instance, if you go to measure the humidity sensitivity of these printed layers, you have a variation in the resistance, okay, with the humidity. And remember that we have carbon fibers and CMC in the printed pattern. And indeed, the CMC, as I mentioned, it's water soluble, so it means that is a hygroscopic compound that will be sensitive to humidity. So it will absorb water from the environment, or the moisture from the environment. And this will affect the way how the fibers connect or touch each other. So let's simplify. So you affect the percolation between the different carbon fibers that are in the film. So, and you are increasing the resistance with humidity. Okay, and of course, the more porous structure responds better to the humidity than the less porous structure. So you see, you can tune the sensitivity by controlling the drying process also of these patterns. The good thing about these sensors, they are also sensitive to temperature. Why? Because the carbon fibers behave like a semiconductor, and then you have the decrease in the resistance with temperature. And they respond differently than to the temperature when you compare with humidity. So they are sensitive to both, but they respond differently. So you can still separate the contribution of temperature by proper training of the algorithms that you use then to make the readings. And of course, you can then decouple the response of the humidity and temperature, because the response to humidity comes mainly from the CMC that exists in the printing pattern, and the response to temperature comes from the carbon fibers. Okay, so the same strategy can be used to prepare semiconducting inks. Okay, and these semiconducting inks can be used, as I will show, both on UV sensors or in transistors. So we use the same strategy. We use a cellulose derivative that can be CMC, or can be another one that is called ethyl cellulose. So you go and modify it again, the cellulose, and you get a powder, in this case, that is soluble in alcohol or methanol, or ethanol, or a mixture of toluene and ethanol, or acetone is also possible. But as I said, we prefer to use CMC because it's water-based system. In this case, we use zinc oxide nanoparticles to mix with the binder, okay? Because we want a semiconductor material or functional ink. And so you can print devices like UV sensors. So you print interdigital electrodes, you print the layer, and you stop here if you want UV sensors, or you can go forward to print the dielectric layer and then the gate electrode to have a transistor, okay? Okay, so some examples. I will not spend so much time in order to keep us on time, but of UV sensors producing cork. In this case, it's not paper, the substrate, it's another natural material, it's a cork surface, okay? And you have here some UV sensors, and you see the response. Of course, you need to adjust the thickness of the layer in order to get to maximize the response, because you see the surface. The surface is a very challenging surface, the cork. It's even more challenging than printing on paper. And so we need to adjust the thickness of the sensitive layer to get the proper response from the UV sensors. You can compare, of course, how they respond comparing with sensors printing on glass that are much smoother. They don't perform so well as those on glass. We know that, but what is nicely is that they can be bended, and in glass you cannot do that. And you see how they behave after bending cycles, and so with a small degradation, of course, but not very aggressive degradation. So is within 10% loss in the maximum current that you get in this on the sensitivity that you get in these UV sensors. You can extend these to transistors. That is even more complex device, of course, because as I mentioned, you have two extra layers. You have the dielectric and you have the gate electrode. And here, just a small note that we are replacing the conventional dielectric, and I will explain later, by electrolytic membrane. So by kind of a solid state electrolyte. And I will explain the advantage of doing this for printing electronic devices. But you see here the paper, and the paper coated with the nanoparticles, and you see the nanoparticles layer that was printed. You see, that is not, of course, a continuous layer. It's made of a full continuous layer, or full dense layer. It's made of nanoparticles with 100 nanometers in average in diameter. But it's enough to create a percolative path. Nevertheless, you have some nanopores in the layer. Okay, so why we use these electrolytic membranes? Because if you compare with the conventional dielectric, and you know, for a conventional dielectric, the capacitance depends on the thickness of the insulating material. Okay, and when you use electrolytic membranes, you get rid of this dependence because you have the formation of what we call electrical double layers. So you have mobile ions inside the electrolyte. You can drive these ions. So if you put a positive voltage in what we call the gate electrode, you drive positive ions close to the semiconductor interface. You accumulate electrons at the semiconductor. It's an N-type semiconductor, the zinc oxide. And basically the charge separation that you have, it's like within nanometers range. And so this brings that it's the same of having a capacitor in which the distance between the plates is just nanometers. So you get a very high density capacitance. Okay, even with a very short, very small voltage, you can accumulate a high density of negative charges in the semiconductor. So you can modulate the conductivity in the semiconductor, or near the interface with the electrolytic membrane. You can modulate the conductivity of the semiconductor in several orders of magnitude by applying a voltage window of like 1 or 2 volts. This is very interesting. Why? Because if you go back, you see the surface, okay? You see the type of surface that you have in the semiconductor layer. So if you put here a conventional dielectric, that in order to achieve a high capacitance, you would need to have kind of few tens of nanometers thickness in the dielectric. It would be impossible to cover uniformly this type of surface, okay? It would be crazy. You will never reach it. So these electrolyte gated transistors are a good strategy of putting here a thick layer that can cover this and still achieve a high capacitance. Of course, this has a problem that I will explain in 2 or 3 slides. That is the maximum response frequency that these devices can operate. Okay, so you can print everything, as I said. So you take the electrolytic membrane, you put it over the transistors, and you can make these simple, what we have here is simple logic gates made of printed devices, printed electrolyte gated transistors. Okay, and here is just an example of an AND door that is basically an inverter. And another thing that we have been doing is also to simplify the techniques or to demonstrate that we can use even simpler techniques to process this. So you can even write some of the components. And here is the example of what was done in the past, not by us, but that already exists in the literature, is writing conductive layers. So you can buy these silver pens, and you have several examples of you can write conductive layers. What is more difficult is to write semiconductor layers, okay? And we have developed an ink that we could put in calligraphic pens. And you see here now in the video, the guy is writing a zinc oxide layer. And you see here in the image, a cross-section of the zinc oxide layer that was created by using these calligraphic pens on top of paper, okay? We also develop in this ink a kind of mixture of a precursor. So you have zinc oxide nanoparticles, and in the ink, we have a zinc oxide precursor. So when you write this ink, you need to heat up to 80 degrees, that is compatible with paper, okay, to decompose this precursor to form also a amorphous zinc oxide layer in between the nanoparticles, the zinc oxide nanoparticles that exist already in the ink. So the crystalline particles that exist already in the ink. And this layer that exists in between the nanoparticles has 2 main functions. Of course, the first one is to keep these nanoparticles together. Otherwise, you just blow on the paper and the particles will flew away. but also to improve the percolation paths in the written layer. Let's call it written layer. Okay, and so you can write also on paper, and you can make transistors using the paper itself as a dielectric. And I will explain briefly also in the next slides how does it work. But basically, you have on one face of the paper the semiconductor layer and the source and drain electrodes, and in the opposite face you have the gate electrode. So the paper is indeed the electrolyte. The dielectric that behaves, as I mentioned before, like a solid state electrolyte, but a very bad electrolyte. And you see that to operate these transistors, you have a large hysteresis window, and you have the need to use like 40 volts to drive or to modulate the current. That is even not that good, the modulation that you get. So I will show some strategies to improve these and to reduce these by 10 times, okay, the operation voltage in these transistors. Okay, so a little about the electrolytes, these electrolytic membranes that we incorporate into transistors. They are also made of cellulose. So it's a mixture of microcrystalline cellulose and carboxymethyl cellulose again, that we need to dissolve. Remember that CMC is soluble in water, but the microcrystalline cellulose, it's like pure cellulose obtained from cotton, is not soluble in water. So you need to use some nasty solvents, or use a strategy that we develop also, that is to use alkali dissolution. So it's basically using lithium hydroxide or sodium hydroxide to dissolve the cellulose. Okay, so we are replacing lithium by sodium hydroxide, but we cannot replace 100% because the dissolution is not perfect under 100% sodium hydroxide. So, but we can go up to a mixture of, we have 95% of sodium hydroxide and 5% of lithium hydroxide. And so you can make this type of membranes by optimizing the composition, and of course getting good flexible membranes, as you see here, electrolytic membranes that are kind of sticky. So we can cut and put over the transistors and behave like a dielectric. So it's a pretty simple way to create the dielectric layer on these transistors. The good thing about this is they have CMC, and if you remember, CMC is hygroscopic. So you can, if you damage these membranes, if you cut, for instance, you can repair them by exposing them to high levels of moisture. And here is the bad thing that I have to say about this type of approach. That is, you have a limitation on the maximum frequency that these devices can operate, because this capacitive behavior, or the formation of the electrical double layers that you get using these electrolytes, it's only possible below 1 kilohertz or something like that. So you see here the impedance measurements, and see that the transition between the capacitive and the resistive regime, that is when the phase angle goes below -45, it's around 1 kilohertz. Okay, so it's basically in principle the maximum operation frequency where we can extend this type of transistors, and this is indeed a limitation, okay, for this type of approach using electrolyte gated transistors. There are some electrolytes where you can extend a little bit more in terms of frequency, because you can tune the ionic conductivity and ionic mobility in the electrolytes, but for solid state electrolytes will be somewhere around these values. Okay, so you see here an example of the transistors with the electrolyte on it. Here a magnification, you see a membrane placed over the transistor. I will not, let's say, spend too much time on this. Also, this is just a comparison on the performance between membranes that were created with lithium and sodium hydroxide. If you just compare the mobility, that is typically the fingerprint of the transistors, this is not so different. The problem with the sodium based electrolytes, and I will skip this slide, when you dissolve the cellulose in sodium hydroxide, is that then you have the tendency to have dendrites formation after some time in these membranes, okay? That you can recover if you expose to humidity, but it's not the best way to do it, of course. But okay, nevertheless, this is just to show that the performance of the transistors can be recovered after we expose these membranes to humid environment to get rid of these dendrites. But the best thing, of course, is to tune the composition in order to avoid the formation of these dendrites. Okay, so I said that we can tune the cellulose fibers to use paper itself as a dielectric, but to operate at lower temperature, lower voltage, sorry. Just also to say that we can obtain fibers from different ways. We can take, for instance, wood and chop the wood and go and separating the fibers that are the constitution of the cell walls of the wood. And you start to have what, microfibers, and you can go down to nanofibers, okay? Or these nanofibers can also be produced by bacteria. So it's a kind of a bottom-up approach. So there are some bacteria that produce nanofibers with less than 100 nanometers in diameter. And these are very good because this is produced by bacteria and it's pure cellulose. While from wood, you need to get rid of some other extractives that are not of interest when you are extracting just the cellulose fibers. And so the strategy to make paper work as a dielectric is this one that I presented before. So you have the paper as a substrate, but also as a dielectric layer. So now if it works as electrolyte, the thickness will not be relevant, as I explained before, as long as you are in the capacitive regime of these electrolytic membranes. You have the semiconductor on one face, the source and drain, and you have the gate electrode on the other face. Okay, so the paper itself, if you tune the properties of the paper to be a good electrolytic membrane, you can use this type of structure. Okay, I will skip these slides because just to say that we can also play with architecture of the devices to go from depletion to enhancement modes in the transistors and create logic operations with just one device. But I will just focus here on the chemical modification of these membranes of nanofibers. So fibers that are less than 100 nanometers in diameter and less than 1 micron in length, okay? By also chemically modifying with some hydroxides. So basically, it's what we call it in a simple way to make ionic doping of these membranes. This has several effects, okay, to improve the ionic conductivity and ionic mobility within these membranes. You see that this is no longer conventional paper because the fibers are smaller than the wavelength of the light and they tend to become transparent. You see, you reduce the scattering of light. But what is more important is that if you use this type of membranes to make the devices, the transistors, you see that the hysteresis now is reduced because we are in a much smaller scale. And the operation of these devices was, in terms of voltage window, was reduced also by 10 times comparing to the previous one that I've shown. Okay. We can go further down in dimension and go to the nanofibers and extract just the crystalline part of these fibers. So if you look for a nanofiber of cellulose, you have what we call crystalline domains. We have amorphous domains where some regions on the fibers where the cellulose chains are not well organized in terms of structure. You can get rid of this amorphous domain and keep just the cellulose, just the crystalline domain by a selective dissolution in an acid. And you get what we call cellulose nanocrystals. Okay? These cellulose nanocrystals have a very interesting characteristic. So if you make a suspension in water, like 3% of these nanocrystals in water, they start to self-assemble. Okay, if you dry the solution, they start to self-assemble in a way, like you see here, like an aromatic liquid crystal. So you see in one layer, you see the crystals align in one direction. They have a small rotation in the next plane, and this continues until they make an alpha rotation. And this continues to make the full rotation. And so it's a kind of photonic crystal, and it has what we call it structural colors. So, okay, and the color that you can get from these self-assembled membranes made of cellulose nanocrystals depends on the pitch of the rotation, and you can control this by the preparation of the cellulose nanocrystals. Okay, so you can make membranes that are green, red, blue, okay, that have these characteristics under circular polarized light. Okay, because it also makes a kind of rotation. You see the self-assembly made a kind of rotation, and this is very good as a filter for circular polarized light. Okay, and you see here, this is a left-handed rotation, and you see that these structures reflect the left circular polarized light. So if you have a filter for left CPL, you see colors. Okay, and if you have a filter for right CPL, you don't see color because the right CPL light will pass through the structure. Okay. Okay, this could be explored, and I will explain later how, but you can also modify chemically these membranes. You see how the cross section, so you see here the crystals with this rotation. The structure is not perfect, and so the pitch is not perfect. And you see here why you can have different colors in different regions of these, I would say, membranes. But there are ways to control it, and we have been working on that. So just not only to control the color, but the drying process in order to have a uniform color all over the membrane. And we can also use these membranes as a dielectric in transistors. So having the gate dielectric, that is the ITO layer here. In this case, is on top of glass. We put these membranes and then we make the devices on top of the membranes. And you see, again, the voltage window, very narrow. And also this hysteresis was in the range of some millivolts. Okay. As I said, we can take profit of these photonic characteristics of the membranes and make it photonic transistors, because these are transistors that will respond both to light and to, let's say, voltage. And so if you shine light, either a left CPL or right CPL on the transistor, the channel layer, so the semiconductor layer, is sensitive to the wavelength. You can tune the response of the photonic crystal made of cellulose to the wavelength where the semiconductor is sensitive. And you can distinguish also the response of the transistor can distinguish between the left CPL and the right CPL. Okay. Finally, energy harvesting. So let's go back to paper, and in this case, just functionalize the fibers with conductive polymer. And the most used is polypyrrole and polyaniline that we are using here. So we can make what we call it these energy harvesting cards, and I'll put here a video running, and you see here the voltage being generated by just tapping on these cards. And I will show you what is the constitution of these cards. So it's fibers functionalized with the polypyrrole or polyaniline, and then you have another paper that has electrode on it, and you have this layered structure. Whenever you punch on the structure, and the mechanism that is proposed for this is a kind of charge transfer, okay, from the polymer to the electrode, due to the formation and local accumulation of charges under the mechanical deformation that will promote the charge transfer to the electrode, and then the relaxation when you release the punch. You can play with the number of cells that you make in parallel or in series to also play with the voltage or with the current that you can extract. And we made a study. I don't have here this slide. I remove it just to keep it simple. But we made a study also on the type of electrode that is better to promote this charge transfer, because of course the Fermi level of the electrode material will be important to maximize this charge transfer mechanism. And so, of course, this is just an example on one of these cards. By punching it, you can light up to 29, in this case, LEDs. Okay, this is just the letters of our acronym of our university. And you see, just by punching these cards, how you can transform mechanical energy into electrical energy. Okay, so to summarize, I will show you just some examples of one prototype that we also developed that basically integrates printed transistors. You see here, printed transistor. This is a printed sensor, okay, temperature sensor. You have here what, I didn't talk about this, but we have here printed electrochromic displays, okay? Everything was printed on paper. The only thing that is missing is a battery that we are emulating with the external power source, but we are blowing hot air here in the temperature sensor. And you see that this change the resistance, this will open the transistor, and you will see a message here appearing in the electrochromic display that is dangerous gas detected. This is dangerous gas because this tag was made for gas detection, okay? But for simplicity and to test it in the lab, we have changed the gas sensor by a temperature sensor, okay? And also one important point that I will not take too much time on this, but of course, this will link with the initial considerations I made about the recyclability. So this is how the transistors can be assembled. Remember, this is the placing of the electrolytic membrane. It's a simpler process, okay? Of course, we are doing this at lab scale. If you go for industrial scale, this could be by lamination. But just to show that at the end, and this is what we can recover these materials. Even the electrolytic membranes that we use as a gate dielectric can recover. And the paper itself, you can slice it. You can make new paper from the electronic devices that you created. You see here the recycled paper, and the electrolytic membranes were recovered and were regenerated and resulted in new electrolytic membranes. You see here the recycled paper, you see here the membranes, and you see how then you can, of course, this being used for other purposes if you want, and the membranes can be reused again for the same functionality. So you can take the central part of these membranes again and reuse it again in new devices. So it's a kind of recycling and reusing concepts combined here. Okay. And then I reached the end. So to thank just to the team that was engaged here. So the 2 postdocs that were working on all these type of things, the PhD students that were working, and these 2 recent guys that are working on the photonic structures and also in the energy harvesting. So they are starting now the PhD. And of course, to the funding agencies that made this possible. And also to thank you, and thank you, Costas, and all of you. And I hope to say it correctly, Sas F Haristo, to all of you. Okay.
Excellent. Nice accent. Thank you, Luis. Thank you, Luis, for this nice, impressive work that has happened as I said at the beginning, in a small country that you have converted your laboratory in a world reference, as a world reference. So please stop sharing the screen in order to check out.
Of course.
If we have questions from the audience. I have some questions. So I can see, thanks from Ioannis Kaliakatsos, Ioannis from the summer schools in Crete. I have some questions. I don't know, if you have any questions, please raise your hand and, switch on your camera and direct the question to Luis directly. We have the phenomenon of the closed cameras, like we are in the lecture room. So I have some questions to you.
Of course.
First of all, I would like to ask you, since we have started some work together, and I would like to ask you, how you can control the porosity of the substrate, either this is cork or cellulose, as a trade-off of the quantity of the material that you are using on top. Because as we have realized, the thicker the material, the higher the conductivity, for example. But since your material, the substrates are porous, a lot of material is intruded, within the substrate. And in order to make the thickness to provide you a sufficient conductivity, this is something, a drawback. So how you can control, the porosity of your substrates in order to not use extra material?
Okay.
This is the first question.
That's a good question, and this I would say it's part of the work that is not here presented. But of course, this was a study, and I can tell you about the different strategies that we have followed. So if you remember these written layers and the cross section, if you notice, the ink does not have a big penetration within the paper. Okay. And you can do it in 2 different ways, by forcing the drying during the printing process.
Luis, I'm sorry about this. This depends, of course, on how is the exodus. How is the exodus?
Viscosity of the ink.
The viscosity of the ink, no?
Exactly. So as I said, it's part of the work that I didn't explain, but you play with the viscosity of the ink, the preparation of the ink. You play with the printing temperature, okay? Because you can print these things at some temperature to force the drying immediately during the process where you're printing, with the solvent that you use, because it may help to dry faster or slow. It's just an example. The ethyl cellulose, where you use a mixture of solvent that is toluene and ethanol, dries much faster than the CMC that is water-based. And of course, depends on the preparation of the substrate that you make. And maybe this is more on the direction of your question. And to do that, as I mentioned, we play with a different dimension of the fibers to have a more close structure. We have even developed papers that are a layered structure that is a more porous structure in the bulk, but in the surface has a layer of smaller fibers that make a more dense structure. When you make the chemical doping, you make what we call it a kind of process that is a mercerization, that is a kind of partial dissolution of the fibers and regeneration of cellulose that basically creates a kind of more closed structure. We can also see this in some pictures that I presented. And for the cork, what we do is to combine cork with the cellulose coating of a coating of these nanofibers on top of cork to make this very smooth layer. So there is a lot of strategies that have been followed, also depending on the type of device that we are talking about. But yes, we did a lot of work on this. We have also a lot of studies done on this. So yeah, it's important point, just to summarize, it's important point to control in order to optimize not only the thickness of the layer, but the quality of the printing layer that you put on top of these substrates.
So Luis, in summary, it's like it can be controlled like during the fabrication of the cellulose, and it also can, through the thickness of the fibers, and also can be controlled by the solvents that we are going to use on the material that we are going to deposit on top. Am I right?
Exactly, yeah.
So I have a second question. I mean, if anyone from the audience has a question, I will provide him immediately the priority. The second question that I have is the following. Regarding the liquid, this chirality that you mentioned, that depends on the thickness or in a simple words, in how many layers that you are going to use of cellulose, if I understood well. So I would like to ask you, I mean, obviously this is directly linked with the distance, of these cellulose molecules in order to make this chirality and use them for photonics application. So what is the minimum or the maximum distance that you can play between two layers in order to have the effect? Because please.
The wavelength where we have the reflection will depend on the distance that it takes to make this rotation, and you can control it. The distance to make the rotation can control it within all the visible range. We even can go in the UV and in the near infrared. So I would say that it's quite straightforward by chemically modifying the crystals to go from 350 to 700 nanometers in the wavelength where you can be selective, because it will depend on the pitch. In principle, the ideal case would be to have a response in a specific wavelength, but as I show, you have not a perfect crystal, so you can kind of spread on this selectivity around the peak wavelength. But yes, you can play with it easily within the visible range.
I was not talking about sorry about this, Luis, and then I will give the floor to my colleague, Dr. Rodakis. I was not talking about the full length in order to observe this vertical change of polarization, but between the layers, because as you can see, you have a gradual rotation of the molecule. So I would like the minimum distance that I was talking about is like between the layers. So if you place an interface, let's say, imagine that you place an interface between the two layers. I mean, this will have an effect depending on the thickness of this interlayer to the effect. The effect indeed to have a selectivity. Okay, if you have just imagine a few crystals that you make a rotation, and you can make the calculation. So the crystals have about 10 to 20 nanometers in diameter, and so if you consider that the thickness, the full rotation happens in 500 nanometers, you can more or less calculate the distance between the crystals. But the important point is that if you have just one layer of the, so imagine that you have few crystals to make just one rotation, and if you have just these 10-20 crystals to make this full rotation, okay,
the selectivity that you get is low because it's in a photonic crystal. You need to have a repetition of this structure in order to have a good selectivity, and as the membrane gets thicker, better is the selectivity that you get between the left CPL and the right CPL. So yeah, the difference in transmittance between left and right will depend on the thickness of this photonic crystal.
Thank you. And the floor, let's say, move to Dr. Rodakis about his question. Kostas, the floor is yours.
Thank you, Kostas. Thank you, Luis, for this nice presentation. I have a question about the maximum speed. So you mentioned that you can go up to 1 kilohertz, let's say.
Yeah.
So usually in microelectronics, you scale down the dimension. So you decrease the length, and at the same time you increase the width of the channel.
Yeah.
So the question is, what is the minimum, let's say, feature that you can print for this kind of electronics, and with which method? And the second related part is about, so the main limitation for the speed is the ionic conductivity. So is there any way to avoid, let's say, using ions for the conductivity and use electrons or holes in order to, to go to higher speeds?
Mm-hmm. Well, yeah.
Yes.
Yeah, it's a very nice question, and I will just answer to the. I will start by the answer to the first one, and maybe then we can get the answer also for the second one. So, yes, as you mentioned, so even in conventional electronics, scale down the dimensions is one strategy to improve the speed, and here is basically the same. You can do the same. This 1 kilohertz indication that I gave, it's just an indication, because indeed, if you go for a real device. This comes from the impedance measurements of the electrolytic membrane. If you go for a real device, you have even less. Why? Because you have another problem, that is, you have a high capacitance membrane over the source and drain electrodes, and if you don't control it well, the positioning of these, you have some parasitic capacitance that limits the operation speed. So it's like in conventional microelectronics. So the overlap also between the source and drain and the electrolytic dielectric is also important. So the dimensions and also this alignment process are critical. The minimum typical features that you can get, and there is now some claims in terms of new printing techniques, you can go nowadays, I would say, below 10 micrometers in resolution. So nevertheless, we are still above 1,000 times above what is conventional electronics. But if you go down to micrometers, of course, you can play a little bit more with the operation frequency of this. But if you go for electrolytic gated devices, you need to be aware that we'll always have this limitation. But I can now answer to the second part by saying, there are already some demonstrations of organic semiconductor devices operating at high frequencies. And some of the devices that were demonstrated were also based on electrolyte gated transistors, because in some cases, they also use this strategy. And it's even worse, I would say, because indeed, in that case, you need to put the ions inside the polymer to make a kind of electrochemical doping, like in P-dot, for instance, it works like that. And you need to remove the ions from the semiconductor. So, and of course, if you have a semiconductor that responds faster to this ion insertion and de-insertion, you can control this and extend this to several kilohertz. I would say that, okay, this will be always a limitation if you use ions within the dielectric to accumulate the charge carriers in the semiconductor. The charge carriers in the semiconductor are electrons, okay? So we are not putting the ions inside the semiconductor. So the ions are driven to the interface, and the ideal case is they do not enter in the semiconductor, that stay at the interface, and they can then accumulate the charge carriers in the semiconductor. The problem is when you remove the gate voltage, how fast they recover to the original position, so to the equilibrium state within the electrolyte. And though this depends on the ionic conductivity or ionic mobility of the electrolytic membrane. The best way to circumvent this is to go for a conventional dielectric. But as I explained during the presentation, on these nanoparticle-based systems, it's very difficult to use a conventional dielectric because the surface of the printed layer is very rough. And if you go to use a conventional dielectric that to have a high capacitance, you need to make it below 100 nanometers, okay? Unless you make things like ALD, that you can get a good step coverage with the dielectric, but ALD is not fully compatible with printing techniques. So you are already introducing a method that is not fully compatible with printed techniques. But if you go for a normal dielectric, to print a very uniform layer of 70 to 100 nanometers is very, very challenging. Of course, I'm talking here about systems that are based in nanoparticles, okay? Why? Just briefly also to explain why. Because when you go for printed layers based on films, it's also possible, starting from precursors, liquid precursors, but typically this needs an extra step, either by thermal annealing or laser annealing to convert the precursor into a film. If you use this strategy, of course, you can use conventional dielectrics with low thickness, okay? But typically this is a different process that involves either longer annealing times or laser annealing or temperatures that are not fully compatible with paper substrates, maybe with plastic substrates. In some cases, it's compatible, but not fully compatible with paper. In this case, all the processes that I have shown are made at room temperature. Even the printing process here or the drying process of the CNC, they are done at room temperature. The only process that I mentioned use temperature is those where we use the written process, where we have there a precursor that needs to 80 degrees to decompose into amorphous phase. But just to say, okay, it depends also on the strategy that you use for the semiconductor layer, the type of dielectric that will be most suitable for this type of devices. Yeah.
Kostas, is it okay?
Yes, yes. Thank you very much.
I lost the story because the answer was long, but you know, I got
sorry.
no. So we have another question, you know, from a colleague, Thanos Piliakos. He has a problem with his microphone and camera. So the question, you know, from Thanos is the following. Let me find it. What is the resolution that can be achieved when using the CF Cellings lithographic methods that you have used? Is it suitable for inkjet printing? By resolution, I refer to print out layer thickness on the Y and Z directions, border roughness, interspace distance, and total area that can be printed.
Yeah. Okay, so to the total area, let's start by the end. Total area. Okay, we are using lab scale machines, but this is fully scalable. Okay, so I would say there is no limitation in the area. Of course, what limits basically the area, or not the area, but the time for the process is that the technique that we use. So if you use inkjet printing, it takes more time to cover a specific area than if you use screen printing or flexographic techniques. Resolution depends on the technique, okay? So I would say the worst case scenario is by screen printing, where you have a resolution, let's say, if you make a line side by side, two lines, okay, you can get easily 10 micron separation, but you can go below can make it 100 micron separation. You can go easily to 50 microns separation under controlled conditions. But below that starts to become challenging. If you go for inkjet or flexographic, you can make it 10, 20 microns line separation. There is nowadays some other techniques being adapted, like reverse rotography, for instance, that are now claiming things close to 1 micron, and also aerosol assisted printed. You can claim already line separation of 1 micron. So in terms of thickness, that you can get in the layers depends again on the technique that you use. For instance, with screen printing, you can get few hundreds of nanometers up to 1 micron in one printing step, depending on the viscosity of the ink that you are using. For flexographic, for instance, or for inkjet, you get some tens of nanometers for each printing step. So you may require more than one printing step, depending on the type of thickness that you need for your layer. So I would say that it depends a little bit on the technique that we are using.
Okay, thank you. I hope that Thanos is satisfied with the answer. And then I have two very short questions. The first one is like regarding your first transparencies that you mentioned about this carbon ink, and you showed that, you know, in one let's say target pollutant or whatever is this substrate is like has a positive reaction. I'm talking about the resistive type of sensors. And on the this was for the humidity, and then for the temperature it has negative coefficient. If I remember well, you know, they have, you know, different kind of behavior. This is like, I suspect that this is the behavior in any material that we're going to use as a sensing element. This is the behavior depending on the pollutant. If it's oxidized or, you know, it's like reducing, you know, it works as a reducing agent, you know, to the substrate. My question is the following. I mean, if you place both of them, you know, this kind of element can be distinguished, you know, what do you have? Because in a separate, you know, if you set up separate targets, this is the behavior that any material will have, no? The difference is like the resolution, the sensitivity, how fast, you know, you are going from on to off. But what did you show to us? Has any discrimination capability when both of the agents are there?
Yeah, as I said, so they are these sensors, these specific sensors are sensitive both to temperature and to humidity, because you have two components in the ink that each of them are sensitive to one of the stimulus. So the CMC is hydroscopic and is sensitive to humidity. The carbon fibers are a kind of semiconductor behavior, and they are responsive to temperature. It will be difficult to distinguish if you have both temperature and humidity changing. As I mentioned, you need to know or to train or characterize the sensors in for each stimulus in the control environment to know the response and to predict the response. If you do this, you can distinguish because they have a different fingerprint in the response of the sensor. Okay, you have a kind of logarithmic change in the conductivity, or you have just a variation of 10% in the resistivity, and one decreases, the other increases. So it depends how you train the sensor. It's important in any kind of sensor, and you know that for sure, that when you go to connect it to something else, nowadays, it's very important how to train the reading electronics to interpret what you are getting. And I would say that, yes, it's an important point to take into account. What you can do is really to understand how they behave under different stimulus and try to decouple the influence.
So you need to do something like calibration and machine learning.
Exactly. Yeah, exactly.
And the last question, because we have to close, is the following: like regarding this kind of somehow like a piezoelectric effect that you have shown us at the end. Like, what is the lowest force that can activate the signal?
Well, you saw here some. We have some difficulty in testing very small forces. Okay, we are tapping this on by hand. We develop a system that it's a kind of free falling weights, and we tested down to 1 Newton. Okay, and I saw this in the slides.
Yes.
It's important. The small forces is important. Okay, and it can go a little. It can go below 1 Newton, but we never tested precisely below 1 Newton. What you see, and also if you look to the slides, is that it's a kind of saturation for higher forces because it's a kind of contact mechanism, okay? And after a certain point, to put a large force, you will not increase the charge transfer process. So because you have a kind of, okay, you cannot improve anything else under the deformation of the structure of the functionalized paper, and also the contact area between the metal and the bottom structure. But I would say that down to 1 Newton is possible. Below, we never tested. Yeah.
So I suspect that this depends on the layer that transfer these electrons, to the dielectric or whatever you had on the top.
Yeah, exactly. So we have studied this for different metals, and also we are now playing with the mechanical properties of the cellulose itself. So it's kind of making a kind of foam of cellulose also to adjust then the sensitive, let's say, the force window where you can use these things. These are based on the kind of triboelectric effect. So it's a kind of contact electrification mechanism. Yeah.
And so this is something like a tunneling effect that happens.
Sorry.
The transfer of the electrons. It's like tunneling effect.
Yes. It's a kind of tunneling. I would say that basically, if you consider that you have a kind of Fermi level in the semiconductor, and you have the Fermi level in the metal electrode. So the mechanism that was proposed is that when you deform the semiconductor, so you have a kind of local charge accumulation. So you move the Fermi level a little bit above, and then you have the charge transfer mechanism to the metal. And that's why it's important to find the right metal also. Yeah. And we studied this between gold, aluminum, silver, copper. So to find the best one that matches that with let's say the maximum Fermi level that you can get in the semiconductor to improve this charge transfer.
Okay, thank you, Luis. I don't know.
You're welcome.
If we have more questions, Yorgos Kavoulakis, do we have? No.
No, that's okay, Kostas.
Thank you. Yorgos is one of the organizers. That's why I'm asking Yorgos.
Okay.
Always. So have a nice day. Enjoy. And we are going to have next week our last one for this semester, for this year actually, of Colloquia Talks. And we're going to have an invited speaker. He's going to speak to us about autonomous driving. So Luis, thank you. Enjoy the summer. I hope that you will visit Crete And if you are in Hanya, just give me a call. I will be
Okay,
back.
thank you, Costas. Thank you, everyone.
Bye.
Bye.
Enjoy.
Bye.
Bye-bye.
Bye. Bye.